So anyways, this is my gear cutting machine. It's pretty straightforward. I built a little U-joint here. I'll show you in a minute how the drill hooks up. All it is some roller bearings with a shaft shoved through it and a spiral tap wedged into here. You could do it with set screws and stuff. I just made a nice fit and drove it in. Then a couple pieces of C-channel aluminum. And then I intersected it with an old Black & Decker drill. Anyways, it just fits in like a U-joint. Yeah, I guess. Take this off. Watch the gear move. You got to support the other end of the cutter because it'll just flex away from the job. So you just, they all have a little countersink in them for the fabrication of the cutter. So you just sharpen up a 1/4 inch bolt and run it in. This is a brass bolt. And it works, it's very stable. Now this gear's already been made, but I will put it on just to give you an idea. Should have something to hold this down, but I ended up just holding my fingers on here because it's trying to pull a disc down towards this stopper. That stopper right there is the ticket to the whole thing. It keeps the disc dead center of the cutter, the top. And then this is just a, I'll take this off one more time. This whole assembly just pivots. It's the same way it's going to pivot when you build the drive with the motor on it. But it'll be a spring on it. So I just put that in there. Oops, that's loud. Bring that into there like that. A little bit more. Tighten it up. And away you go. You're making teeth. Always mark where it first bites in. Give it put the cutter pretty harsh into the material so that it starts to grab. Once it starts driving itself, it'll self-feed. Make a mark so you can always check these last 4 teeth to see if 4 or 5 teeth to see if they're getting munched. If they're getting munched, just keep cutting deeper. Believe it or not, there was no calculation. I've done 10 of these gears now and I never did any math. They just self-find their own. They just you just keep cutting deeper and eventually where the joint is, you won't even see it. And let's see now. Yeah, this is a 1/2 by 13 threads per inch tap. Spiral tap. If you use a straight flute tap, it'll just chug and chug and chug and eventually you'll break a tooth or so. This is continuously engaged because it's spiral. 13 threads per inch. Just going to move that in a little deeper. We'll run it a bit more. And then over here I got a finer tooth gear I built, a larger diameter. And it's 1/2 by, I wrote it down here, I think it's 1/2 by 20. Spiral tap, same thing. Spiral tap, just got to find one of those at machinist shop or parts place. And this is the ready rod I used to build my drive. It's a ready rod or a bolt. And you just got to get a motor on the end of this. And it sounds simple, but it isn't. Coarse thread, 1/2. Here's a fine thread. Whoa, keep making a lot of noises here. And that turns on that one. Anyway, It just gives you an idea. These are 80 thou in thickness. Same aluminum I used on the 40-pounder project and a lot of my other projects. You get it at a scrap yard or even buy it new and use a router with a carbide tip and some lubricant, and you can cut a nice disc and then drop it on a machine like this and slowly feed it in. After so many turns, you adjust this a little bit more and you keep monitoring that spot. And when that looks good, you stop. You're done. Anyways, this can drive you can build any size disc you want. It could be 20 feet in diameter. The gear could be in the center shaft of the gear could be in the middle of the room, because all you're working is this one little area. You're just working here. Diameter means nothing. So you could drive your dobsonion in Altitude and Azimuth on DC motors. Dead simple. For visual aid only, mind you, get involved, but I did it all really simple. All runs on penlight batteries, the whole scope. Anyways, that's the gear machine.